Recently, I read an interesting paper from Song and Peric about hash visualization as a technique to verify overlaid keys. I won't go much into the details, but basically it says that humans are pretty slow and inaccurate at verifying or comparing meaningless key strings, right? So let it be SSH keys, etc. And there could be an alternative that replaces these with structured images for this verification. And what caught my eye specifically is this random art algorithm developed by Andre Bauer as a possible solution for hash visualization. And you probably already seen one implementation of this technique if you ever use SSH keygen command. So if you run SSH keygen, is that ed as you can see, SSH keygen generated for us this random art image, ASCII image. I'm not sure if people use it that much, but that's basically the idea, right? To have this visual representation of your key. The basic idea of this algorithm is to provide a seed string to our pseudo-random number generator. This randomness is then used to generate this expression tree. And then for each point of the image, each pixel, we evaluate this tree. And because we seed our pseudo-random number generator with the seed phrase, we can ensure that for each phrase or each key, we will always get the same image as a result. Now let's review the algorithm. So the random art algorithm has three inputs, G, I, and D. G is a grammar. It's a set of all possible operations that comprise this expression tree. In this example, it's basically the math formulas, so sinus, mod, mixing color, so everything you can imagine you can do in this tree. And obviously, it can be different for each implementation. I is an initial rule, so it can be fixed as constant, could be also randomly generated as basically the root of our tree. In this case, it's sinus, for example. And then depth is basically the depth of our tree. Higher the depth means better results, but also slower execution of this function. Also, if we look at these operations, they can have inputs. For example, there is a mix here, mixes the colors. There are also terminal operations, which are the leaves of our tree. They don't have any inputs, so they could be constants, let's say, or maybe they can just generate some random number and then move up to the tree. And then how it works, as I mentioned before, let's say we want to draw a square. For each pixel in this square, we will evaluate this tree with some input parameters, and then it will result in RGB colors, and then we will export this as an image. The author of Random Art algorithm also published this page, which I believe uses his Python implementation. So you can see the kind of images his implementation can generate. You can try it on your own. It's actually quite slow, probably because it uses Python. I'm not sure, maybe there are other reasons. I've also seen implementations in C++ and WebGL implementations, but haven't seen a Go implementation just yet. And that's what I want to do in this video. We will explore the pseudo-random number generators in Go with seeding. We will use, obviously, the standard image package to actually output the image. We'll build this expression tree, build some operations, maybe not all, but hopefully enough to see some cool images as a result. Let's get started. I want to explain this expression tree a little bit more. So here's the example of the expression tree that has been generated for the given depth, which is 3, and some phrase, right? So the phrase is only needed to seed our pseudo-random number generator that will then randomly select these nodes. So we start with color mix. Color mix basically mixes the colors of 3 inputs. So the arity we can tell of this operation is 3. What our algorithm now should do is to pick the 3 random operations as inputs for this node, right? So we pick, let's say, smooth mix, mod, and product for our given phrase. And then we go kind of one level deeper for the smooth mix, we also need 3 inputs. And then we go to these terminal operations, which don't require any inputs, like var x and var y, constant, for example, and maybe there are a little bit more. They can just, output some number, then will be then used everywhere else. And yeah, we will try with higher depths, obviously, so the tree will be a little bit bigger, so hopefully we'll see some nice images. Yeah, but that's what we'll now need to implement in Go. But let's first start with the kind of main program, right? With some inputs like depth and phrase, and then have a function for building this expression tree. Obviously, we'll need to implement all these expressions as mathematical functions. Yeah, let's get started. Let's design this program as a command line application with some flags, so we can easily pass the needed depths and the phrase. So, right, the phrase will be string. It could be, let's say, some key, and depths as well. Remember, higher the depths, probably the slower the execution, but also better results. All right, and now let's populate these variables from the command line flags. Use the flag package for that. String var start phrase, and then maybe similar for int var, the depths. And let's set default as 5. And now we can just run flag.parse, I believe. Now let's write some skeleton code for creating the image and then exporting it to a file. So we don't have the expression tree yet, but we can start with some kind of skeleton, right? As I mentioned, that for each pixel we'll need to evaluate the expression tree, so we can already write some loop here. And then we do the same for and then somewhere here we'll need to set the color of the pixel, right? So say color, and then let's say it's all set. Actually, no, let's create an image first. For that, we can use the image package, and I believe there's this new, so we'll be using RGBA. That needs a rectangle, so let's create this rectangle bound. So top left, the image point 0, 0, and then similar for bottom right, will be width and height. And I believe it's image rectangle. Yeah, I believe we can do something like that. Awesome. So somewhere here we'll set the color on this image, and then we'll need to create a file, right? Image.png, and that will be png.encode. Right, file and our image. Now, since this is ready, let's dive into pseudo-random number generation in Go. And you probably already know about the rand package, and that's obviously what we'll be using here. There are other solutions as well, but that should be enough for our use case. So let's create a function that pseudo-random number generate, right? So that will return us this seeded random generator. So because it's seeded, we need a phrase, and it will return, I believe, rand dot rand. I'm not sure if it's a pointer. Awesome. So if you used rand before, there is a possibility to seed the random generators. I believe it's let's say it will return rand dot new. It needs a source, so I believe it runs new source. The problem here is that the seed is integer 64 and our phrase is a string. So what we need to do is to convert somehow the string into the integer, and we can do it by I mean, it's not ideal, but we can get an MD5 of our phrase and then convert the MD5 to an integer, kind of not ideal, but that will be enough for this exercise at least. And if you're interested to know more about pseudo-random number generators and these algorithms, you can have a look at Mersenne-Twister algorithm. That could be used here as well. And so let's continue with our MD5 solution, right? So MD5.new. We can write there the phrase. Now, how to convert MD5 to integer 64? I mean, it's probably impossible, but we can use the, let's say, I believe it's binary dot big endian in 64 from byte, so h sum. Why this is not ideal? Because this function, if we open that, it takes only the first 8 bytes, right? So MD5 obviously is longer, so this is not ideal, but enough for our exercise, right? And yeah, we can pass it then here. Let's just make it comment. Not ideal. Now we can get an instance of our pseudorandom number generator with this function. And I want to show how it works, right? So we seed it with the phrase. We get the phrase here. Let's say pseudorandom number generator, this function, and then we pass the phrase. So, and then we can use these Go functions from the rand package, like get the random integer in this range, etc., etc. So, for example, right, let's say integer, right? I want just to print it to show how it works, right? So let's just call it 3 times, for example, here. So let's say we run our command with the phrase package main, right? All right, these are big numbers, right? Anyway, see these huge numbers generated, right? Now, if I run it again with the same phrase, I should see the same numbers, and exactly, I see them as well the same, right? So they are randomly generated, but because they've been seeded, we can ensure that for the same phrase, we always get the same results if we go in sequence. But if I go and do something else, say Golang, right? So these values will be different, right? Cool. So now we have this pseudo-random number generator. We'll be using this to generate our expression tree. But first, we need to understand, kind of define what is the operation in this tree, build some interfaces, and kind of implement some before actually recursively building this tree. Okay, so let's define the operations in the separate file. Say operations.go, and then we'll start with the operation interface. So type operation interface. Now, as I mentioned before, the operation can be a terminal, so there are no inputs. There should be an evaluation function on this operation, then basically a way to set the inputs. So let's create few methods there. One is that returns the inputs count. So we expect the small inputs count, so it could be unsigned integer 8. Then the method to set inputs, and here basically we provide the list of operations. It doesn't return anything. So imagine we have a color mix operation that mixes the colors of 3 inputs. So the inputs count in this case will be 3, and then the set operations, kind of when we call this function, we'll need to send 3 inputs for this node. And then the most important function is eval, which takes the 2 parameters always, x and y. In the beginning, we will send the basically kind of the pixel index, but we'll convert from 0 to 1 float, and then y the same. But it returns. So let me write this first. That returns the RGB colors. But since we kind of do this computation, we always work with float 64, and then at the end convert this to RGB, which are from 0 to 255, as I believe. That's basically our interface of the operation. It will be just a little bit easier to understand when we create some implementations of this interface. So let's start with some simple operations. I mentioned there are some terminal operations like constants and x and y. So let's do the operation x and y and constant, and you'll see it a little bit better. So for example, option rx is a struct that implements that, right? So what do we, because it's a terminal operation, it returns 0 inputs count. So when we do set inputs, basically it does nothing. And all right, so that's not correct. And eval function and that's why it's called X, because it will set the RGB colors as X only. So the return will look something like that. Float 64, X, X, X. So here's the simple operation implemented. And bear with me, we'll have a lot, so I'll probably have to speed up at some point. But imagine we'll have operations that call mathematical functions to draw circles, etc. And so we have x, we can do the same for y. Just, all right, so I think this is not correct. So inputs. Let me do the same for y. Absolutely the same, but it will fill this RGB result as y only. So this is an example of 2 terminal operations, right, that don't have any inputs. Let's see, I already mentioned the color mix. So we have in our graph here on the root that has 3 inputs that are randomly generated. And then it mixes the colors. So it takes 3 inputs and then picks 1 color from input 1, then second color from input 2, and the last color from input 3. So let's call it operation color mix, right? The inputs count, so that's what we need to set 3, and then set inputs. To do that, we'll have the inputs defined on the struct, so it's basically the slice of operations, and then we can do simply here. So All right, not S, O. So this part will be the same for all um, kind of operations that require multiple inputs. Um, the color mix will be different though. So because we have three inputs, we call recursively, so we'll call recursively eval of these inputs. So let's say we take so RGB red, right? We take red from the input one. So we take 0 inputs 0 dot eval, we pass X and Y there, right? And then we do the same for RGB, just inputs 1 and 2, and we return RGB. Make it more beautiful, let's just do it here. So they're called R and G and B. Great. So I'll fill more operations, but then now, since we have the interface, let's think about how to pick the random operation and create the function for that, then use our pseudo-random number generator here. So let's call it pick operation. What we'll need to provide here is our pseudo-random number generator, just run.rand. Then we need also the depth. Why we need the depth here? Because we want to kind of, if it's the deepest level, then we only want to return the terminal operation. So to randomly pick only the things like var x, var y, and constants. So I'll fill them more here, and this will return the operation. And this function will be basically a factory that, depending on the depths and random generator, returns the random operation. And we should define here the terminal operations. Maybe let's give them kind of the ID or the code, so that could be X and Y. At the moment, there'll be much more here at the end of this video. And then all operations, that would be X, Y, and color mix at the moment. So we have the string ID, sorry, the operation ID, and then, so now that's how we use the depths, right? So if the depths, so the depths actually in this case will be reversed. So we can do if the depths, so if we didn't reach the terminal depths, the latest one, we can do the prng dot int n, right, and then length of all operations. Then op ID will be all ops from y. Otherwise, we only take the terminal operation. So that would be here, terminal ops and terminal ops here. And now we can do the simple factory here. So d, and then let's say case x, return that op var x, and then the same for color mix. Maybe for the default, I don't think it will happen, but we can return an error here or panic. Invalid op ID and return nothing in this case. Cool. So for our three existing operations, we have a function that picks one random for a given depth and prng. Now we can go back to our main.go file and actually build this tree, right? So going recursively, As you remember, in the algorithm, we have the initial operation or initial rule. So that would be the root of our tree. So, and we can just hard code it as color mix. So, for example, we always want color mix to be kind of the root node, right? So color mix. But we need recursively to set the inputs of that node. So we can do root.set inputs, and here we need to generate them and then do it recursively. So we will have a function generate, let's say nodes, right? And this function needs, so our generator, it needs the count of nodes that we need to generate. So for color mix, for example, we will pass 3, so count, and I believe the depth, and it will return the slice of the operations, right? So it's not implemented yet, but then let's see how we'll be using it here, right? So set inputs, root set inputs, generate nodes, PRNG. Then how much do we want to generate? It's root inputs count that will return 3 in this case, and then the current or the needed depths, right? So basically these will generate the expression tree. We just need to do this generate nodes. So in the beginning of this function, we don't need to return any operations if the count is 0. So you can do that. Return operation. Actually, maybe we don't need this. We'll see. Now, yeah, actually, I don't think that we'll need this because we will just iterate over it and it will be empty. So let's do a loop. And here we'll use our pick function, so to pick the random operation from our grammar. So pick operation, right, PRNG, and current depth, right? Now recursively, to fill this, we need to set inputs, which would be, yes, our generate nodes function, as we did before, right? So generate nodes, PRNG. Now, how many nodes do we want to generate? We can figure out this from our operation. So inputs count, and we do depths -1 here. Now ops, so append it to the ops here and return the list. So let's see how it works, right? So we start with color mix. Then set the inputs, which calls this generate nodes. And we know that for color mix, we need 3 inputs. So it will get 3 random inputs. It could be color mix again there, could be X, could be Y from these grammar of operations. And then it will recursively set inputs, can generate these nodes again. Now let's go back to our pixel loops and actually call this eval function of this expression tree. And then set the color, and hopefully we can already see some images, but they won't be beautiful because we just have these 3 very simple operations, but let's give it a go. So as you remember, our eval function needs X and Y, but it needs them in float and from 0 to 1. So we can convert the pixel index or the row and column index to this 0 to 1. So X in it would be, let's say, like that. Same would be for Y. So these are just initial X and Y. So we can do it this way. We can maybe have another formula. It doesn't matter that much because then the expression tree is big enough so it will modify these values many times, but we need some initial x and y to provide. And that I believe should be enough, right? Now let's get our RGB from, we start with the root, right? So we already have this root, and then we call eval, and it pass x and y. Let's do like that. Awesome. So we have our RGB also in the float type. And here's how we can set the color. So we can use this set. Yes, X and Y. And then color would be called RGB. But RGB and B are in unsigned integer 8. So that's how we can convert this. Let's say R would be, so RGB 0 to 55. And also, just in case it's bigger, we will do something like that. So G, yeah, so these, I believe, could be also replaced with something like 0x ff, I believe. So that's the same. And now let's set RGB, and the last one is alpha, and we can just do 255. Okay. Cool. So we set the color of the pixel. I believe we do it right. We do eval. We create the image. Awesome. Now I just want to confirm that all of that works and we actually get an image, and you know, it has some colors at least on that. So let's run this phrase Golang, right? So the depth is 5 by default, but let's actually so you know that you can provide it here. 5. Cool. So I already had the image PNG here, right? You see there is some color mix happened here, X and Y. Awesome. So that changes. Now this is boring images. Let's actually have some circles here, maybe some other elements, and to do that we need just more operations here. So let's go back, and here where I'll speed up a little bit, I'll code them quickly, and then we'll just go into the we just read through them and I'll explain what they do. Okay, so I extended our grammar to have more operations. Now let's have a look at what we have. So we already had var x and var y, also added the constant. Basically, when we initialize this struct, we provide some randomly generated constant, and yeah, fill this RGB with this value, right? Color mix we already had. Also added the circle operation. This is very nice. It basically uses the Euclidean distance between the x and y. So we use the hypod mathematical function. We use inverse. Basically just inverses the colors, basic sum, product. We have a binary mask. We have the, it's called well, so it's kind of similar well looking because it uses the power function. And that's it, right? So I also added them here to the pick operation. and this switch changed a little bit because so before we only simply returned the kind of instance of our struct. Now, for some operation, we also need to provide a constant or maybe generate the randomly the center of the circle threshold. And basically, that's it. So the rest of the functions stay the same. So we only have a little bit more operations. It will be, yeah, now really exciting to actually see, yeah, how that works. Can we generate something better here? Cool. So now I'll be running this command multiple times and hopefully find some cool looking images, right? So as always, yeah, depth 5 and then phrase. Let's start with our Golang. Cool, so that's the image generated for the Golang. Maybe I'll just run a few things and then see if there is something really beautiful. Also, as you can see, it takes a bit longer to generate the image. Oh, this one is cool. Wow, this one, I like it. I could kind of, if I have a key that generated this image, then, for comparison, I could kind of remember that. Yeah, maybe we need some massaging around these operations, maybe remove some, or maybe add more. This one looks interesting as well. Yes, C3. Now let's just confirm that for C3, it returns always the same image, so we run through the same command. Yep. Is the same as you can see. Obviously, if I change the depth to something else, the expression tree now will be different, so smaller or bigger, and then the results will be different. So let's try with the kind of a little bit slower, but let's see. It still, by the way, will be similar. So if you change the depth from 5 to 6, still will be similar because a part of the tree will be similar or identical because we use the same phrase. So our pseudo-random number generator seeded in the same way. I could use it as a background image. Wow, this looks nice. Awesome. I originally found this algorithm through this hash visualization paper that shows that the user security can be improved by taking human factors into the account. I'm not sure if it's really applicable in the real world. We've seen that something like that is used in SSH keygen, but this random art algorithm is quite interesting, right? It can generate really beautiful images. And yeah, I put all this source code in the description so you can play with that, run it on your own, maybe also change the grammar a little bit, add new operations, and yeah, let me know if you can generate really nice images. I'm not sure, share them somewhere with me. Cool, thanks a lot. See you later. Bye.